Section 4.3 is all about quadratic functions and their properties. So friendly reminder that a quadratic equation can be written in the form ax squared plus bx plus c equals 0. So this is an example of a quadratic equation. So it should be f of x equals this, right? This is an example of a quadratic equation where a, b, and c are real numbers and a doesn't equal 0. Okay, this is called a quadratic equation. It's a function because it passes the vertical line test. Its domain goes from negative infinity to positive infinity, and its graph looks like a parabola. All of the fun facts, right? The domain of a function is all of its possible x values, and the range of a function is all possible y values. For a quadratic function, its domain is going to go from negative infinity to positive infinity, but its range varies depending upon how the quadratic, what the formula of the quadratic equation is. So a function is a quadratic function. Okay, yeah, this was right. A function is a quadratic function if f of x equals ax squared plus bx plus c, where a, b, and c are real numbers and a doesn't equal 0. Because if a equals 0, then it wouldn't be a degree 2 equation, so it'd be a linear equation. It wouldn't be quadratic. The graph of a quadratic function is a parabola, and every parabola has a vertical axis of symmetry through its vertex, and we're going to talk about identifying vertexes today. So here's my favorite quadratic function, right? It's just the squaring function. What it does is it takes each x value and matches it with its square. So negative 2 goes to 4, negative 1 squared is 1, 0 squared is 0, and so on. Its domain goes from negative infinity to positive infinity, and its range goes from 0 to infinity with 0 included. Its vertex is 0, 0. By vertex, I mean where it looks like it switches from going a decreasing function to increasing function, right? We have a change of direction. So the axis of symmetry is x equals 0. This line right here down the middle. Remember, we could shift our parabolas vertically if I have f of x equals x squared and I add or subtract a constant. That's going to shift my graph either up or down along the x-axis. So if I have our example, f of x equals x squared minus 2, this is my squaring function, but it's shifted down 2. Next, I can also shift my parabolas horizontally, right? If I have f of x equals x minus h squared, that's going to have the same shape as f of x equals x squared. It's going to be shifted h units along the h axis. So, for example, if I have f of x equals x squared minus 2, right? It's our graph, but it's shifted instead of to the left 2, it's shifted right 2. That means my new vertex is when x is 2, y is 0, and my axis of symmetry is when x is 2. Suppose f is the quadratic function f of x equals ax squared plus bx plus c. If I rewrote our function f to be f of x equals a times x minus h squared plus k, where h is negative b over 2a, and k is f of h, or 4ac minus b squared over 4a, then our quadratic function is in vertex form. So let's practice by finding the vertex of example 1 here, which is f of x equals 2x squared plus 8x plus 5. So I need to find my h first. I always want to start by labeling my A, B, C's. So I would have H equals negative 8 over 2 times 2. That gives me negative 8 divided by 4, which is negative 2. I then take F to find my K, which is the other point of my vertex. So that's important to note. Okay, my vertex, HK is my vertex. So I want to find the vertex, and then I could also write these in vertex form if I wanted. So K is f of H, so I'm going to take f of negative 2. That gives me 2 times negative 2 squared plus 8 times negative 2 plus 5. 2 times 2 squared is 4. 4 times 2 is 8. Minus 16 plus 5. I'm going to get negative 3. So my vertex is when H is negative 2, y is negative 3. So I could rewrite this function in vertex form. I could have f of x equals 2 times x minus a negative 2 squared minus 3. That would be the vertex form of this function. All right, let's take a look at f of x equals negative x squared minus 9. That negative leading coefficient tells me my parabola opens downward. Let's find our h. H is negative b, which is 0, because my a is negative 1, b is 0, and c is negative 9, over 2 times negative 1. I'm still just going to get 0. So if I find my k, which will be f of h, which is f of 0, I get negative 0 squared minus 9. So I have minus 9. Cool. So I could rewrite this in vertex form as f of x. So that's my vertex when x is 0, y is negative 9. I write this as negative, because negative 1 is my a, x, no h, right, because my vertex is 0, squared minus 9. So friendly reminder, our vertex is hk. H is negative b over 2, and then if I substitute that into my function, I can find my k, which is f of h. I'm going to have a line of symmetry at h, so when x equals h, or when x equals negative b over 2a. If my parabola is concave up, that means a is positive, and my vertex is my minimum. So if it's opening up, my vertex is the lowest value. If my parabola is concave down, when a is less than 0, so it takes on a negative value. This one was positive. The vertex is my maximum point, right? And there is no minimum. So let's find the vertex of a parabola by completing the square. This is a little bit of a different method. Okay, so what we're going to want to do is if a doesn't equal 1, we want to pull out a factor of a from our terms, okay? Then what we're going to do is we're going to want to square half of our coefficient x and add and subtract this to our equation because that will add to 0. If we add b plus 2 and subtract b over divided in half squared, then it will be like we're adding 0, so we haven't changed our equation at all. Then we can factor the trinomial as a perfect square and combine our remaining constants. So f of x equals x squared minus 4x plus 5. Well, my leading coefficient is 1, so that's cool. What I'm going to do is I'm going to go ahead and I'm going to add b divided by 2 squared, which is negative 4 divided by 2 squared. And subtract b divided by 2 squared. I add 5, because we can't forget about our constant. I know that this is going to factor into a perfect square. So I'm going to have f of x equals x minus 2 squared minus 4 divided by 2, negative 4 divided by 2 is negative 2, Negative 2 squared is 4. 4 plus 5 would be a positive 1. So my vertex is the point 2, 1. Why don't we go ahead and check if we're right? Let's go ahead and graph this original function in Desmos. So if I go into Desmos and I type in f of x equals x squared minus 4x plus 5, which was our equation, we can see that our vertex is right where we said it was going to be. Our vertex is when x is 2 and y is 1. Right? And our vertex is where our graph changes direction, so it switches from a decreasing function to a increasing function. So let's go ahead and look at this second example. I have f of x equals negative 3x squared plus 6x minus 1. So let's open a new page. Now this parenthesis is unnecessary, so I'm going to get rid of it. And what I need to do is I need to go ahead and pull out a factor of a, which is negative 3. So I have f of x equals negative 3 times x squared minus 2x minus 1/3. And what I now have to do is add my b term divided by 2 squared. So we'll add negative 2 divided by 2 squared. And we will also subtract negative 2 divided by 2 squared minus 1/3. So I have f of x equals negative 3 times this part right here, which factors into a perfect square. So that factors to x minus 1 squared. Negative 2 divided by 2 is negative 1. Negative 1 squared is 1. So I got minus 1 minus 1/3. So I have f of x equals negative 3 times x minus 1 squared. And then I also have negative 3 times this portion over here. I'm pulling apart. I'm undistributing. So I have f of x equals negative 3 x minus 1 squared. Negative 3 times negative 4/3 gives us a positive 4. So my new vertex is when x is 1 and y is 4. Let's go ahead and graph this to make sure we did it correctly. So if we go to Desmos and graph our function, we can see that if I have f of x equals negative 3x squared plus 6x plus 1, that vertex is when x is 1 and y is 4. And because it has a negative coefficient, this parabola opens down. Its range is from negative infinity to positive infinity, just a little refresher. And its domain goes from negative infinity to 4, and 4 is included. And 4 here is a maximum point. Now we're going to work through a couple examples where we find the vertex of a parabola using our vertex formula, right? Because nobody wants to have to complete the square all the time. So first thing we do is identify our A, B, C's. Here I have that H is negative B over 2 times A, so I get a positive 2. I also see that my I can find the other part of my vertex, which is K, by substituting H in for our function. So I'm going to find f of 2, which would give me 2 squared minus 4 times 2 plus 5. So 4 minus 8 would be negative 4 plus 5 would be a positive 1. So my vertex is when x is 2 and y is 1. For this next equation, I have f of x equals x squared minus x minus 6. So my a is 1, my b is negative 1, and my c is negative 6. So if I have my h, that'll be negative 1 divided by 2 times 1. That'll be a positive 1/2. So I plug that in. If I have f of 1/2, I'm trying to find my k, the y value of my vertex. I'm going to have 1/2 squared minus 1/2 minus 6. So that's going to be 1/4 minus 1/2 minus 6. So I have negative 1/4 minus 6. 6 is 24/4. So I have negative 25/4. So let's use the vertex formula. In order to graph the following, I want to state their domain, range, line of symmetry, and maximum or minimum. So h, my first part of my vertex is going to be negative b over 2a. So I've got negative 2 over 2 times negative 3. That's going to be negative 2 divided by negative 6 is a positive 1/3, so I'm going to have negative 1/3. And then my k is f of negative 1/3. So that equals negative 3 times negative 1/3 squared minus 2 times negative 1/3 plus 1. So that's going to give me negative 1/3 squared gives me a positive 1/9 times negative 3 gives me negative 1/3. That's negative 2 times 1/3 gives me a positive 2/3 plus 1. So I am left with 1/3 plus 1, which is 4/3. So my vertex is negative 1/3, 4/3. So x is negative 1/3, y is 4/3. So it's right about here. I know that my line of symmetry is x equals 1/3, negative 1/3. That's my line of symmetry. And my minimum is my vertex. My domain is negative infinity to positive infinity. And this parabola has a negative leading coefficient, so it's going to open down. So my range goes from when x is, it goes from y being negative infinity all the way to 4/3, and 4/3 is included. Now it's important to note when you're graphing a parabola, I want you to graph at least 3 points. If you didn't do that in the last exam, it was okay, but I need you to find a couple points. So let's find f of 0. So negative 3 times 0 squared minus 2 times 0 plus 1 is just going to be 1. So when x is 0, y is 1. And let's try negative 1. If I have f of negative 1, that's going to be negative 3 times negative 1 squared minus 2 times negative 1 plus 1. So I get f of negative 1 is a positive negative 3 plus 2 plus 1, that's 0. So here's going to be my skinny little parabola, and its line of symmetry is right through its vertex. I'm going to go ahead and clear the board so I can work on this last problem. Alright, so let's go ahead and work on f of x equals 2x squared plus 4x plus 5. I'm going to go ahead and label my A, B, C's. H is negative b over 2a, so I have negative 4 over 2 times 2, which would give me a negative 1. F of h will be f of negative 1. That's going to give us our k value. So right now I have my vertex is negative 1, but I don't know what the other point is. We'll find that out. So I get 2 times negative 1 squared plus 4 times negative 1 plus 5. That gives me 2 minus 4 plus 5. 2 minus 4 is a negative 2 plus 5 is 3. So I have when x is negative 1, y is 3. I need to find a couple more points. F of 0 would be 5. F of negative 2 is going to give us 5 as well. So here I have my 2 points. My minimum is my vertex. My line of symmetry is x equals negative 1. My domain goes from negative infinity to positive infinity, and my range goes from 3 all the way to positive infinity. We can also use the vertex form formula to find a function given its vertex and another point. So if our vertex is hk, and I'm given one additional point on my quadratic, I can use this form, f of x equals a times x minus h squared plus k, to obtain the quadratic function. So what we're going to do is we're going to plug in our points and then we can solve for a. So how do I do this? So I have f of x equals a times x minus h squared plus k. So I know my hk, so I have f of x equals a times x minus 1 squared minus 5. I plugged in my h and my k, but I also know this other point. I know my y-intercept. So that's when x is 0, y is negative 3. Y being f of x, and x just being x, I can plug those in. So I have negative 3 equals a times 0 minus 1 squared minus 5. Negative 3 equals a times negative 1 squared is 1, so a minus 5. If I add 5 to both sides, I get that 2 is equal to a. So I can write my function f of x equals 2 times x minus 1 squared plus my k, which is minus 5. Let's try another example. So I have f of x equals a times x minus h squared plus k. I have f of x equals a times x minus h, which is the first term of my vertex, squared plus k. And I have an x of negative 1 and a y, or f of x value of negative 8. Negative 8 equals a times negative 1 minus 1 squared plus 4. Negative 8 equals negative 1 minus 1 is negative 2, negative squared is 4. So I have 4a plus 4. I subtract 4 from both sides. I get negative 12 equals 4a. I divide both sides by 4. Negative 3 equals a. So I have the function f of x equals negative 3 times x minus 1 squared plus 4. And if I wanted to get this vertex form in the more standard form, I could go ahead and FOIL this out to put it in standard form.